Swayam Prabha. Digital India. Educated India.
My next presentation is that chemical reaction kinetics. Now, in the last class, I discussed how the different chemical reactions we can write the rate equations for the different type of reactions, and you can remember that I told you that that if you look at the biochemical process, then mostly the reaction that take place, either they are reversible in nature, and also they are the chain reaction. In the microorganism, we have metabolic pathways. In the metabolic pathways, that you have a series of reactions, and you have different steps, and in the different steps and individual steps are we have that reversible in nature. So, we try to, in the last lecture we come across the reversible, and in the reversible reaction we have forward reaction, we have backward reaction, and we have come across the equilibrium constant Kc, which is nothing but equal to concentration of product divided by concentration of substrate. Then also in the chain reaction we try to establish that how the concentration of different component in the reaction mixture can be expressed. That in the chain reaction we have different components A, B, C, D. So, how these components will keep on changing with respect to time, and how we can develop the equation for that. Now, today I want to go little bit more on this, and you will find that other type of reaction that we have parallel reaction. Parallel reaction means that this is the substrate, same substrate, maybe it is producing two different products. This is R and S. So, if you have this kind of two different products, so we call it parallel reaction or side reaction. Then your rate of substrate that degradation can be expressed as K1 into Ca plus K2 into Ca, and you can Ca take the common K1 plus K2. Then rate of formation of R you can always express as K1 into Ca, and rate of formation of S you can, this is parallel reaction also we can write like this. Another very interesting thing is that autocatalytic reaction. What is autocatalytic reaction? Where A plus R and produce R, and R is the product, and R itself again acts as a catalyst to carry out the reaction. So, that is why we call it autocatalytic reaction. And if you take into account in the microbial system, particularly is largely applicable. In the microbial system, what is happening, particularly in the Baker's yeast fermentation process, we use sugar for the formation of cell mass. Now, sugar is converted to cell mass, and again cell mass, they again utilize the substrate and producing the cell mass. So, this is a kind of autocatalytic reaction we can take into account. Now, if you have that kind of reaction, how you can express? This is Ra equal to minus dCA by dt equal to K into Ca by Cr, and C0 is the initial concentration. It can be expressed as Ca plus Cr, Ca0 plus Cr0 is a constant, and rate expression can be written like this. So, this is how we can express the autocatalytic reaction. Now, I am going to discuss some problems. Now, first problem that I want to discuss, that is let us assume the reactant A decomposes in a batch reactor A to B, and the composition of the A in the reactor is measured at various time with results showing in the table. Find the rate equation to represent the data. This is very simple, simplest this problem that we have. what basically what I told, suppose this is a reactor. We have reactor, and what is the reaction we have? A to B, am I right? So you take the A in the system, A you take, and let the batch process, you take the material at a time, let the reaction take place. Now at different time you draw the sample and find out what at different time what is the concentration of Ca. That has been given in this problem. So you have to find out the rate equation. What is the rate equation? Actually we have shown you this is rate expression for this will be minus dCA by dt equal to K into Ca to the power n. Am I right? Where K is the rate constant and n is the order of reaction. So we still have to find out both these things. So if you want to do what we still have to do, that we can take a log here. You can see you can take a log here, minus dCA by dt equal to n log minus sign I can take it here, ln Ca and ln plus ln K. There I can write like this. And if you plot log graph paper, now what we can plot, this is one end I can plot ln minus dCA by dt, and this is ln Ca. If you do this, you will get a straight line, and slope, this is slope, will give you the value of n, and this intercept will give you the value of ln K. So you can find out the A and K value. So in this problem, how you will solve, I can show you. So here you see that we have different C, and we find out dCA by dt. Now how you calculate the dCA by dt? Let me show you. Minus dCA by dt, I can calculate like this, equal to Ca n plus 1 minus Ca n minus 1 divided by 2 del T. This is called differential technique. This is called differential technique. Very simple. What is the n? Is the sampling number. Sampling number. So you have, suppose here you put n, and in 1, 2, 3, 4 like this, you can have different number, and this is, so n you see that here Ca n plus 1. Now if you consider here n plus 1 means at this point, if you want to calculate minus dCA by dt, how we can calculate? How we can calculate that Ca n plus 1, that means you have to take the value here Ca2, then Ca n minus 1, that means 1 minus 1 equal to 0. So initially at the 0 hour, whatever the concentration is there, you find out, and that difference, and 2t del T, what is the time difference? Del T is the time difference, you multiply that, very simple, you can do that. So you can write this value. This is how this table has been prepared. This is we have these values, then we take the log value, and then log Ca value is given there. Then we can have log graph paper, we plot this, and we find out the value of the K value is 0.55, N value is 0.41, and so your equation is coming like this. Now I want to add little bit here, because suppose this equation is coming like this, dCA by dt equal to minus 0.55 Ca to the power 0.41. Okay, so we get the value of K, we get the value of N. Now here this is the correlation between Ca and T. So I can write this, how I can write this equation? dCA by Ca to the power 0.41, this is equal to minus 0.55 into dt. So, you can easily find out, we can find out the correlation between Ca. Now, we can put the value at different time, we can find out the value of Ca. So, what you can do that the Ca value, we have already determined that in the Laplace system that experimental value we have, this is the experimental value. Now, we can calculate theoretically also, and we can assume the t, we can assume the value of t, and we can find out the corresponding value of Ca. So, this point I can write it here. We can find out this is the what you call theoretical value. And then compare with the experimental value and try to find out the deviation. And if your deviation is more than 5%, then this equation is not valid, but if it is less than 5%, then we say the equation. This is called what you call modeling and simulation. That also I want to point out, this is, I can elaborate this like this. The second problem is very interesting, that milk is pasteurized if it is heated to 63 degrees centigrade for 30 minutes. We know pasteurization. What is pasteurization? The pasteurization is process through which we can remove the pathogenic organisms. Okay, and but if it is heated to 74 degrees centigrade, it only needs 15 seconds for the same results. You know that there is a technique called HTST technique. What is the HTST technique? High temperature, short time. This is usually applicable to the industry. Why? Because if you use the HTST technique, then the quality of the product we can maintain to a great extent. And what in this problem, what you have to find out, the activation energy of this sterilization process. Very interesting that problem that we have. So, what is the data given that at 30 minutes at temperature T, this is the 63 degrees centigrade. So, equivalent Kelvin temperature will be 336 degree Kelvin. The 15, then this is 15 seconds. This is the mistake. This is 15 seconds, and this is will be 340 seconds. So, please make the correction here, and this equation is like this: k equal to k0 e to the power Ea by RT. What is k0? It is Arrhenius constant. Ea is the activation energy, R is the gas constant, this is the absolute temperature. Now, I can write this equation like this, and reaction time we have already seen. What is the reaction time? Rate of reaction minus dCA by dt. Reaction time always inversely proportional to time. If the time time is less, then the rate of reaction should be high. They are inversely proportional. If the time is more, that means the rate of reaction will be less. So, this is so we can write ln K2 by K1 equal to ln T1 by T2 A R and 1 by Ta minus 1 by, then we can find out that Ea equal to 42200 joules per mole. So, this is the activation energy of this reaction. So, this is simple way how we can calculate the activation energy in a chemical reaction. So, if anybody interested to find out the activation energy of a chemical process, that they can easily find out if they have the data with the at different temperatures. The next problem that I have, the liquid A decomposes by first order kinetics. Liquid A decomposes first order kinetics in a batch reaction. 50% A is converted at 5 minutes run. How longer would it take to reach 75% conversion? So, the reaction is the situation is something like this. So, you have A to B reaction that we have. So, what is saying, the 50% of A will be converted in 5 minutes. Am I right? Now, what then the question comes that for the conversion of 75% of A, how much time is required? Okay. How much time is required? Okay. So what we have done here, you just see that minus RA, as you rightly we know that the minus dCA by dt, K into Ca. We assume this is the first order. This is already mentioned first order kinetics. Now this is this is the range between Ca0 to Ca and K into dt. This we can write ln Ca by C kt. Then we have come across this equation Ca equal to Ca0 1 minus Xa. Xa is the fraction of A that is converted. So we can come across this equation, and finally we can write that the conversion of A, this is the T2 and T1, the two time conversion, and if we take the ratio, and finally we can find out the T2, that is coming about 10 minutes. So 75% initially that the question was that 50% conversion take place in 5 minutes, 75% conversion take place, how much time is required? Answer is 10 minutes. So it's very simple that we have. So we can easily calculate this that if you know if you can do the analysis of the system, and this is very much required for our biochemical processes, because there our substrate is converted to product, and we are interested that to find out that how much time is required to get the desired conversion of the product. That that is that we time to time we can find it out, and I have several problems that there we can find out which one is economic. If we go for 99% conversion, whether it is economy or 90% conversion, we have some problem. We can discuss in due course, and we can do the analysis of the process. Now the last problem that I am going to discuss, that is I told you the biological process is a chain reaction, A to R and R to S. So we have two rate constant, one is K1 and K2. Now what do you have to find out, that at T0 Ca equal to Ca0, Cr0 equal to Ca0, that is the equal to 0. To find out the maximum concentration of R, and when it reaches Tmax, when K1 equal to K2. So what is here, what we are basically looking for, that we have seen in the chain reaction, when we have the profile with respect to time, this is the concentration, then this Ca will keep on decreasing with respect to, this is A to R, R to S. So this Ca will decrease with respect to time like this, then R will decrease like this. This is Cr, and if you look at Cs, this will be like this. This is the Cs. The concentration of C will be like this. Now what we are in this problem, what they are looking for, here this is the intermediate concentration of the product. Now question comes, at what time we can attain the maximum value? This is called, what is this? This is called Cr max, and here we call Tmax. The Tmax is the time at which the R, the intermediate concentration of the product, that will be maximum. So this problem deals with that. Let us, and at the same time they mention that what will happen when K1 equal to K2. Now let us see this how we have solved this problem. Now we know the rate equation. This is RA. This is the RA equal to that dCA by dt minus the K1 into Ca, RR equal to this, and this is rate of forward reaction, this is rate of backward reaction, and R is equal to K2 into Cr, that we have seen in the last class. Now here that that when you take it the first reaction, that we have already seen that minus dCA by dt equal to K1 into Ca. Am I right? So, we can write minus dCa by Ca equal to K1 into dt. Now, here this is equal to dln Ca minus this is equal to K into dt. So, this will be what Ca0 to Ca, and this is 0 to t. K is constant. So, what we can write ln minus Ca by Ca0 K into t. So, the Ca by Ca0 will be what? Will be e to the power minus kt. What will be Ca? Ca equal to Ca0 into e to the power minus k into t. So, we can easily find out this is how it has find out here. We can easily see that. And now, if you come to the next step that we have, the rate of formation of that that odd, that how it is. So, we have this equation already. We have this equation. How we can write that dCr by dt plus K2 into Cr. Am I right? This is equal to K1 into Ca. This is what we have done in the last second case. This is like this. Now, the Ca, this is K1. Ca we determined Ca equal to Ca0 e to the power minus K1t. Okay. Now, if we multiplied both sides, now here what is happening? K1 equal to K2, K21 equal to K2. So, and multiplying both sides by e to the power K1t. If we multiply it by this, what will get? We will get this equation. We will get this equation. This is e to the dCr by dt K1 into Cr e to the power this, and this is and this. Now, here the e to the power K1t into e to the power K1t minus K1t, if this will they cancel each other, this will be 1. Am I right? And so, this will be what? This will be nothing but this equation. If you look at that, e to the power K1t dCr by dt K1 Cr e to the power K1t, this is plus equal to K1 Ca0. Am I right? That is cancelled. Now, here this is nothing but d e to the power K1t into r Cr by dt. This is equal to K1 into Ca0. Okay. Now, if this equation, so what we can write now, the e to the power K1t into Cr, here Cr equal to K1 Ca0 0 to t, this plus constant. So, this we can write like this. Now here we can put the boundary condition. What is the boundary condition? Boundary condition is that at t equal to 0, because we have seen that profile that this is like this, this is Ca and this is you have Cr. So, here this is the 0, this is time, this is concentration. So, at time t 0, I can assume Cr equal to 0, so this is equal to 0, and if Cr equal to 0, then this will be 0, this constant will be there will be equal to, this is the K1 constant will be 0. because this is also 0, this is also 0, so constant will be 0. So your whole equation will be what? Equation will be CR will be equal to what I can write, CR equal to K1 CA0 T e to the power minus K1T, because I took this the K1T this side, so it is minus K1T. Now if you come this side, then if you do the differentiation dCr by dt, how we can do that? What is the two variables we have, this and this? So we can write K1 K into CA0, I can take this, and this is differentiation with respect to t, this will be minus K1T Kt, not K1T, because K1 equal to, I can write K1 equal to K2 equal to K, I can write like this. So it is K Kt, then we have minus, then what I can write, that T will be there, and this will be K1 T into e to the power K1 T. This we can write this, and this is equal to 0, because if you look at here, that CR by respect to time, that at this particular when T max, the CR by dt, this will be rate of formation of CR, that should be equal to 0, that will be under steady state current, this will be 0. So this is the condition. So at T max it will be 0. Now this cannot be 0. So if this cannot be 0, I can assume this is equal to 0. So I can write e to the power minus Kt equal to K1 into T e to the power minus Kt. Am I right? This will cancel. So I can write the T equal to 1 minus K. This we can write. So this is the T max value. Now this T max value, now we have the expression for already we have the expression for CR. Those I can write CR max. How we can write? CR max equal to K into CA0. T is the what? 1 by K e to the power, this is minus K multiplied by 1 by K. So this will cancel, this will be minus, and this will cancel. So I can write this is CA0 to the power E. So and E value is this is the equal to 0.3678 into CA0. So I can easily calculate the value of CR, what is the maximum value of CR, I can easily calculate in this particular problem. So in conclusion, I want to tell that it is possible to write the rate equations. It is any kind of rate equation we can easily write. We can also find out rate constant. We can find out the order of reaction, and then we can because this is very much required to find out the correlation between the substrate concentration and the time, because when you carry out any kind of reaction, we are interested to find out at what time we have what percentage of substrate conversion take place. Suppose I was talking about that in the industry, when you carry out any kind of reaction, that naturally most of the industry we are looking for the efficient process, and efficient process we wanted to have higher substrate conversion efficiency. Now when you go for the higher substrate conversion efficiency, we require more time. Now question comes whether it is economic or not. So that we shall have to find out, and for that the preliminary thing that we should know that how to determine the time required for that conversion. I hope this will be very useful for you for finding out the time required for getting a desired conversion of any kind of chemical or biochemical process. Thank you.